That is a famous, well-known song called Sweet Georgia Brown, used by the Harlem Globetrotters as their theme song. But it's Sweet Georgia Brown. It goes way back to ragtime days. All right, so here is the third part of the video that we're going to start. And what we'll be looking on the third part is something generally you talk a little bit about in college algebra, and that's the endpoint behavior of polynomials and what we call the leading coefficient test. The reason this is useful in calculus is if you see a polynomial function, then you have the ability very quickly, just in your mind, takes you less than a second to know what the limit at infinity is of a polynomial function. So I'm going to open up this applet and just kind of roughly show you what this is and talk through this a little bit. This is a Desmos Applet that's online. So what this shows you is that how the degree of a polynomial affects what the graph looks like. So this is what we call a fourth degree polynomial, and the number in front is positive. If I put like another positive number in front, it kind of squeezes it together a little bit. But look what happens if I put a negative in front. Okay, well, then what happens is the polynomial turns upside down, say. Okay, and that's the kind of stuff that you learned in college algebra. So if you got an even degree and a positive number in front, then that's what your graph looks like. Throw a negative in front, you learn that that reflects that. Okay, well, look what happens if we chop this off and just have a third degree polynomial. Now, when you have a third degree polynomial, that is what we would call an odd degree. And when you have this odd degree polynomial like this, okay, it usually is going to swing up in that direction and swing down like that. Okay, if I make that number in front negative, then it changes everything. Okay, it swings up this way and swings down that way. So it's kind of a nifty little app to just kind of play around with. Now see if I go back to a even degree. Well, it's just straight up or straight down. Okay, so that's what that applet shows you. What I'm going to go through is what we call the leading coefficient test, that just kind of quickly shows you how the endpoint of behavior of a graph is going to go. All right, so there's four things that can happen just to start with. So if the highest power is odd and the leading coefficient is positive, then it looks like this dancer right here. Okay, so what that means is if x goes to infinity, so does y. So the graph just kind of swings up like that at its endpoint. And then over here, if x goes to negative infinity, y swings down also to negative infinity. So they kind of go in the same direction like that. And in a polynomial function, it may connect in several ways. It depends on what the degree is. It may have different, minimums and maximums like that. But what we're concerned about is this. X gets big, y gets big. X gets small, y gets small. That's the way an odd degree polynomial works if the coefficient of that highest degree is positive. So here's an example. This is really what matters. On a polynomial, all that really matters is the highest power. The rest of it can kind of be ignored. So because that number in front is a positive number, that's what causes this to do this, and the fact that it's an odd polynomial. Okay, next page is when you have a odd power, the highest power is odd, and the leading coefficient's negative. So that would be like this disco guy right here, all right? I was alive during the disco days. I remember those days well. All right, so here's what happens. Okay, basically if x goes to infinity, y goes to negative infinity. Okay, it just means x gets big, y gets small. So that means as you're going to the right, the graph goes down. Okay, over here, it means if x goes to negative infinity, then y goes to positive infinity. Okay, so what's going to happen here is as x gets small, y gets big, And again, they may connect in different ways depending on what that degree is. But if it's an odd degree, it's going to behave that way. Again, this example on the bottom, that's what matters. The highest power matters. The rest of it doesn't really affect how the endpoints behave. It affects how other parts of the graph behave. But that right there determines the endpoints like that. Okay? All right, so that's an odd degree and a negative leading coefficient. Okay, next two cases are if you have an even function and the leading coefficient's positive. So in that case, even polynomial, positive leading coefficient, looks like this dancing girl right here. What it really means is as x goes to infinity, x gets big, y also goes to infinity, so that gets big as well. So that endpoint is going to go like that. Okay, over here, if x gets small, x goes to negative infinity, well, y still gets big. Okay, so it goes like that. Now, what I want you to kind of understand on this thing is what matters. Okay, and what happens if you put a big number, even if you put just say 100, 100 to the 10th power is big. And if you do negative 100 to the 10th power, well, that negative becomes positive, so it's still big. So really, if you forget this, what you could do is you just look at the highest power, plug a big number in, plug a small number in, and that'll tell you how the endpoint behavior goes then, all right? Okay, and the last case is this dancing lady here. And the idea here would be if you have an even degree polynomial and a negative leading coefficient, it just means if x is going to infinity, it's getting big, then y is going to negative infinity, meaning it's getting very small. So you're going to have a graph going like that. Over here, if x goes to negative infinity, so if x gets small, then y also goes to negative infinity, so it gets small as well. And again, these things may connect and kind of do this kind of thing. They're a function. That's not what we're really too concerned about. So the idea is the only thing that matters is this. Okay, again, if you forgot how this goes, if you put in a big number, like if you put in negative 10 times 100 to the 8th power, you're going to get a negative number. Okay, so it's getting small. And if you put in a small number, like a negative number, if you do negative 10 and then times negative 100 to the 8th power, it's still negative. Okay, so see, it's just the 8th power, the even power, makes any number positive. But then if you multiply it by negative 10, it gets negative. Okay, so you want to try to make sure that you understand that best you can, then you won't forget it. Okay? All right, so what I'm going to have you all do is just do this on the next page. I'm going to have you fill this out yourself. And you don't want to get your graphing calculator out. Just look at these 4 cases. Tell me if it's an even or odd degree polynomial, what the leading coefficient is, draw the graph, and then see if that's enough information for you to figure out what those limits are. Okay, so I'm going to let you go with these problems. And go ahead and pause the video. And then as soon as you're done and want to check your answers, then just resume it. Okay, so here's what I hope that you came up with. It's just a matter of knowing how each polynomial works. This one is an odd degree. Highest power is 3. Number in front is negative. So that graph looks like this. And again, what this says, if x goes to negative infinity, this just means if you're going to the left, y goes up. So the graph's going up, so it's positive infinity. If x is going to infinity, so if x is getting big, then y goes down, so it's negative infinity. Okay, that's what you're worrying about. Okay, the next one is an even degree polynomial. The highest power is 4. So it's an even degree. The number in front's positive. That means the graph does this. This just means you're going up. So that would mean the limit of both of these is going to go to positive infinity. Okay, it's getting bigger forever. Okay, down on these, the next one is a 5th degree polynomial, so it's odd. The leading coefficient, number in front, is positive. So what happens is as you go to the right, you go up. So the limit as x goes to infinity will go up to positive infinity. And then if you go to the left, the graph goes down. So if x goes to negative infinity, the limit is going to negative infinity, like that. Okay, then the last one, you have an even degree. 2 is the highest power. Number in front is negative. That means it's kind of like turning downwards. So basically what's going to happen is in both directions, the limit is going to go to negative infinity. So as x gets small, y gets small. As x gets big, y gets small also. Okay, so that's what you want to do on that is if you're doing a limit of a polynomial at infinity, you don't need to graph, you just need to know how these polynomials behave graphically. Okay, the next thing I'm going to show you, this is something you'll see probably on your homework, that sometimes kind of throws students a little bit, is this. Okay, so we're doing limits at infinity, and anytime you do a limit at infinity, if you're asked to do a limit as x goes to either plus or minus infinity, you really think about a horizontal asymptote, if you have one. That's what your focus becomes. Now this one right here, without graphing, this is what the way I want to explain this is like this. If x is really small, then this really doesn't make that much difference in the function value. So you can really just ignore that 4, okay? If you take a really, really small number like negative 2 trillion and square it, okay, that 4 isn't going to make much difference to anything. So you can ignore that, and then you can think of this as square root of x squared over 2x. Well, you know that the square root of x squared is x over 2x is this. That crosses out, so you're going to be going to 1/2. Okay, so that's how you can figure that out, is work out the algebra. You can kind of ignore that 4, and then that'll pretty well tell you what's going on in the problem. Now, you can only do that because you're interested in either negative infinity or positive infinity. Okay, you graph that on the calculator, that's definitely what you're going to see. Okay, over here, now again, think of this one like this. This goes along with what we learned. Okay, this is really 5x to the 1/2 plus 2x to the first minus 1 over x to the first minus x to the 1/2 plus 2. So the same rules apply. The degree of the numerator is 1, because that's the biggest power. That's bigger than a 1/2 power. The degree of the denominator is also 1. So what happens is you look at the leading coefficient ratio. So it's right there. So what you get is you get a horizontal asymptote at y equals 2 over 1. So that's y equals 2. That means the answer to that limit's 2. So that's the same thing. Don't let the square roots bother you. The degree of the top in that case is going to be 1, and so is the degree of the bottom. Okay, and that's how that goes. Now, what I would highly recommend that you do as you're learning these kind of problems is, try to do them yourself. Don't get your calculator out, but do that to verify. So I'm going to verify this first one. We have square root of x squared plus 4. And then that's going to be divided by 2x. This is not a rational function because it has a square root in it. Now, here's something that you need to pay attention to. If I put it in this way, that's not correct. 2x has 2 terms, so that right there must be in parentheses. Okay, that goes in like that. Now, if I go zoom 6, graph this in a standard window, we kind of get a graph that looks like that. Well, what's happening is as x gets smaller and smaller, and what you can do is just kind of look at your table of values, and look what happens as you get smaller and smaller. You're going to see all these 0.5s everywhere. Okay, and you know 0.5 is a half. So as x gets small, y gets closer to 1/2. Okay, so that's what you want to know and get out of that. Okay, the next one, again, you could verify this one. Let's put this in the calculator and let's see what this one looks like. Okay, so in parentheses, I'll put 5 times square root of x, like that, and then plus 2x, and minus 1. And divide by, and let's see, this will have x minus square root of x and plus 2. and make sure those are numerator and denominator are enclosed in parentheses. Graph it in a standard window. And again, we're looking at x goes to infinity. So again, if you look at your table of values on this, well, you got all these errors. You know why we have those errors? Because you can't do a square root of a negative number. So that's why I'm asking for the limit as x goes to infinity. Well, just scroll down on here and kind of see what's going on. Okay, it's taken it a while, but you can see it's getting smaller and smaller and smaller. It's going to level off it too. I could sit there and here and do this all day, and eventually it's just going to get closer and closer to 2, but it's getting closer to 2 at a slower rate. Okay, so I'm going to just pause at 316, and hopefully you believe what I'm doing on that, okay? All right, so go ahead and pause the video and do these two problems. Reason them out yourself, and then if you want to go to the graphing calculator to verify it, then please do that. Okay, so this is what I hope that you came up with. The first one, the answer is square root of 2. The second one, the answer is 3 over 2. The way you reason out the first one, as you kind of think of it like this, you can what really makes a difference is 2x to the fourth. That overpowers the x minus 1. Because remember, we're putting in a infinitely big number. Okay, and if you take infinity to the fourth power, that like way outperforms, in a sense, the x minus 1. So the x and 1, you can just kind of ignore it. And same thing with the denominator, the 1, you can just ignore it. So what I did is I looked at square root of 2x to the fourth over x squared. And if I work that out, the square root of x to the fourth is x squared. Then that divides out. So that's how you get square root of 2. That's how you can reason that out. These things right here can be ignored. Okay, because when x is infinite, that ain't going to make much difference, okay, in the grand scheme of things, all right? And what happens on this number 1 is the graph looks like this, and I went ahead and just said, okay, look what's happening. As x is getting real big, that's getting close to the square root of 2. And on a calculator, if you do the square root of 2, you'll get close to these numbers right there. It looks like it's just the same thing forever, but that's not really the case. What's happening is it's just sort of truncating the decimals. So if I do square root of 2, you see the 1.414, but technically with more decimals, these things are not the same. They're just getting closer to the square root of 2. Square root of 2 is an irrational number. Its decimals repeat forever without a pattern. Okay, the second one is just about the degrees. You could write this as 3x to the first minus x to the 1/3 over 2x to the first plus x to the 1/2. The degrees are equal, so since the degrees are equal, then 3 over 2 is the horizontal asymptote. Okay, you can see down below how I put it in my graphing calculator. This is what the graph looks like in a standard window. And again, what's happening on this is getting close to 1.5, which is 3/2. So you can see on that one pretty well that it's just getting closer and closer to 1.5. Okay, so that's a pretty good way to look at that problem, particularly that number 1. It's good to be able to reason out in your head what that limit is going to be. Okay, so the goal on a lot of what we're doing in this section is to be able to do the limit in your head, to understand functions good enough that you can do that in your head. Because this kind of thing shows up in higher math. You'll see a lot of this if you're going to take a Calculus 2 class. Okay, so pause the video there if you need to look at that. And then what I'm going to do is I'm going to go ahead and we're going to do example 10 together, and then I'll have you do a problem kind of like this, and then that'll wrap up what we're going to be looking at in this section. So now we're just kind of looking at limits. So I'm going to go ahead and zoom on this so I can see this a little bit bigger. So x goes to infinity. That just means as x goes forever to the right, x is going to infinity, y is getting close to -2. You have this horizontal asymptote. That's what's happening. Okay, if x goes to negative infinity, okay, that means we're going this way. Well, look at the graph. What's the graph doing? It's going up forever. So that limit is going to positive infinity. It's just getting bigger without limit. Okay, now what we have on this next row is we have a vertical asymptote. So we're interested on this row at what's happening on this graph when you have that vertical asymptote. Okay, this one, the first one is a right-hand limit. So get on the right side of that asymptote, -2. And what happens, anytime you have a vertical asymptote in a rational function, the graph gets closer to it and either just goes straight up or straight down. That one's going down, so that one would be going to -infinity. Okay, the left-hand limit, get on the left side of the asymptote, and as you get closer to the asymptote, that graph just gets bigger forever, so that goes to +infinity. Okay, and then since the left and right hand limit are not coming to the same value, then this one would not exist. So that's how you'd reason through that. Okay, now this is not the graph of a rational function. This is probably the graph of a piecewise function. So the next one, if we look at the vertical asymptote at 2, so this is, we're looking at 2. So if I just highlight that vertical asymptote, then we're going to look at this the same way. Okay, this is a right-hand limit. Okay, if we come from the right, as we get closer and closer from the right, that thing goes up forever, so that one is going to +infinity. If we're coming from the left on this, now this goes like this, that's getting closer to a y value of 0. And that's not a rational function. If you have an asymptote of something other than a rational function, something like this is possible. But this is probably likely a piecewise function. Okay? All right, and then again, these are different. So the two-sided limit does not exist. All right, so pause the video if you need to think about that a little bit. It's all a matter of looking at the right place on the graph, and remember the answer to a limit is a y value that you are approaching. Now that can be infinity. Okay, so let's wrap this up. Last page, go ahead and go here. Go ahead and do these problems. Pause the video, and then resume when you're ready to check. You know, I just caught a mistake on this. I mean, it's okay, but I think this one was intended to be x goes to 2, x goes to 2, and x goes to 2. That was my intention on that. It's not that you can't do the problem. It's just if you were doing the right and left-hand limit at -2, there's not an asymptote, so that's not really what we're studying here. So go ahead and correct that, and you can redo that problem. Okay, now I'm going to go ahead and just put this together since I made a mistake in typing that up. Okay, so x goes to infinity. As x goes to infinity, that just means x is going on forever. That just gets closer to the y-axis, so you have it gets closer to 0. The same thing happens on -infinity. It just means as x gets smaller, y gets closer to 0. You can see how it levels off, so that's equal to 0. Okay, now we get into the asymptote on this one. So I'm going to highlight this asymptote, and this goes like this. So this is a right-hand limit. If you're to the right of that asymptote, trace it out. That's going down forever, so that's -infinity. Okay, your left-hand limit, get on the left-hand side. As you get closer to the asymptote from the left, that's going to +infinity. All right, and then we know that the two-sided limit does not exist because the left and right-hand limits are different. Okay, then the last one, it looks like we're looking at a vertical asymptote at x equals 6. So I'll do just kind of the same thing. I have a left-hand limit here, so if I come from the left of 6, that's going down to -infinity. If I come from the right of 6, that's also going to -infinity. Okay, they're both going down, so that means if the left and right are both -infinity, then so is the two-sided. Okay, so that's how you think through that. It's just, again, a matter of the x value tells you the part of the graph you're observing, and the answer to the limit is the y value you get close to as you get closer and closer to that x value. However, sometimes it just gets out of control and goes to infinity. Okay? All right, so I hope you enjoyed the video, and hope you get everything wrapped up and do a good job on this section. Let me know if you have questions. Cheers.